Welcome back. In the previous videos, we learned about substitution reactions of an alkyl halide. In particular, we focused on SN1 and SN2. Okay. In here, we are going to focus on elimination reactions E1 and E2. Okay. As you can see on the screen, E1 and E2 share a lot of similarities with a little bit of differences when compared to an SN1 or SN2. Okay. Let's look at the similarities and then we'll talk about the differences. Okay. E1 reaction shares a lot of similarities with SN1 in that, similar to an SN1 reaction, an E1 reaction rate depends only on the concentration of the reactant and not on the nucleophile. Okay. While it may not depend on the concentration of the nucleophile, it does depend on the nature of the nucleophile itself or the solvent in which the reaction is carried out, which we would look at down the road. But as far as just the reaction rate goes, it does depend only on the concentration of the reactant, and it's not depend and is independent of the concentration of the nucleophile. Okay, but we would learn that whether a base or nucleophile is stronger or weaker does have an impact on whether a reaction would be favored in an SN2 E2 direction or an SN1 or E1 direction. Okay, with that said, it is unimolecular, so that's what the 1 stands for. That is, it only depends on the concentration of the reactant and is independent on the concentration of the nucleophile. Okay, reaction mechanism involves 2 steps, and this is directly related to this. You know, when we learned about our SN1 reactions, we did learn that SN1 reactions go through the formation of a carbocation. Now, what did we learn about a carbocation? Which is a carbon attached to 3 bonds, okay, and a positive charge. Okay. Now, if all the 3 bonds are not hydrogens, then we call it a tertiary carbocation. Let's say we have a carbon and one of them is a hydrogen, the remaining 2 is not, and a positive charge. We call that a secondary carbocation. And then you have a carbon with, say, 2 hydrogens out of the 3 bonds. Okay. One of them is not, then we called it a primary carbocation. And say the carbon contains all 3 bonds as hydrogens with a positive charge, of course, in the middle. We called it a methyl carbocation. Okay, and the stability is, if your reactant contains a tertiary substrate, then you will have a tertiary carbocation. If your reactant contains a secondary carbon substrate, that means it will lead to a secondary carbocation. For instance, say your reactant looks like this. Okay, we know our Cl group is our leaving group and our CH3 is our substrate. You can see that if the Cl leaves, okay, and you end up with a positive charge, then that will be a methyl carbocation. However, we know that because methyl carbocation is a very weak carbocation, we rarely ever will have a methyl carbocation. It would almost be SN2. Okay, methyl primary would rarely ever go through SN1 or E1. Okay, I'm giving that to you now. Okay, it's only the secondary and the tertiary that can fall either directions, but we will look into that more detail as we go more. Okay, just like an SN1, an E1 also involves the formation of an intermediate. Now, what is the intermediate? The carbocation itself is the intermediate. So let's write that down. The intermediate is the carbocation. Okay, now all this I've said for SN1. If you're not sure, you can go back and watch the video again. And E1 reaction is generally common among a substrate that's tertiary. Okay, however, some secondary substrate also go to a certain extent to produce E1 products, but predominantly if your substrate is tertiary, that it is a carbon containing 3 bonds and neither of them have a hydrogen, then that's called tertiary. Typically, that would lead to an E1. Okay, we would look at an examples. Now, it all comes down to the nature of the nucleophile, which we would see in the next few slides. Tertiary substrates and weak, bulky nucleophile. Okay, we have not really focused on this as much, and that was for a reason. Okay, we're going to focus on this in more detail as we go through. Okay, a tertiary substrate and a weak nucleophile. The bulky is very important because some nucleophiles are small, some are really, really big. Okay, typically bulky nucleophile favors elimination. Okay, if it's a tertiary substrate and a weak, bulky nucleophile, it favors E1. If it's a tertiary substrate and a strong, bulky nucleophile, it favors E2. Okay, again, I will summarize all this in my flow chart, but it's a good thing we talk about those in the context as we discuss these things. All right. So just like E1 shared a lot of similarities with SN1, E2 shares a lot of similarities with SN2. That is, the reaction rate of an E2 depends on both the concentration of the reactant and the nucleophile. For instance, say if this is our reaction, okay, plus say your OH minus. Now keep in mind, this is just one of the many nucleophiles available. Okay, we're going to look at a variety of nucleophiles today, and then how those nucleophiles can help us determine whether we will have an SN1, SN2, E1, or E2. Okay, so and this leads to products. Okay, so if you write the reaction rate, now we do know that this is a primary, right? Sorry, this is a methyl alkyl halide because it's a carbon attached to 3 hydrogens. So that's rate equals rate constant. And then, of course, it also depends on the concentration of the nucleophile, right? So this is a generic rate expression. What we have here is actually for this particular reaction. Now, in this case, because the molecule is too small, I'm able to write it this way. If the molecule is really large, you would have to concise the carbon, hydrogens, and other elements separately into a concise form and write it. I'll show you another example if you need it be. And the reaction mechanism involves a single step. That is, it's a conceded reaction. Remember, everything happens all in one go. As the nucleophile attacks the carbon containing the leaving group, or in other words, as the nucleophile is getting attached to the carbon substrate, the leaving group is also getting, the leaving group is exiting at the same time. Okay, does not involve the formation of an intermediate. That's one of the major differences between E2 and E1, similar to SN2 versus SN1. Okay, it only involves the formation of a transition state. Okay, don't mix it up too. All chemical reactions have a transition state, but not all chemical reactions have an intermediate. So E2 reactions does not involve the formation of an intermediate. It only involves the formation of a transition state. Now, E2 reaction is very much common among carbon substrates that are either tertiary or secondary. Okay. Okay. We will see some examples as we get going. And tertiary substrate, if you want to be absolutely sure that your reaction should only happen via an E2, then you should have a carbon tertiary substrate. And in comparison to a E1, where we said it was a weak, bulky nucleophile, if you have a strong, bulky nucleophile, then it would favor an E2. Okay? Now, this is something very important from a test perspective. Okay, now, whenever an elimination reaction happens, it's usually the beta hydrogen that comes up. Okay, now you need to know where those beta hydrogens are. So alpha, beta, and gamma are the three types of hydrogens, as you can see here: alpha, beta, and gamma. Okay, alpha, beta, and gamma. Right? Now, depending on the functional group itself, where the alpha is located is always different. Right? Now, if you look at this particular compound, this C double bond O is your functional group. Okay? Because when you have a double bond, it's already got 4 bonds. There's no hydrogens here. So the carbon adjacent to the carbon containing the functional group, so it's this and this, okay, on either side. Say if it is completely on the end, then you would only have 1 alpha carbon, but because it's in the middle, carbon that's immediately adjacent on both sides is the alpha carbon, and it's whatever carbon that contains that, the alpha carbon contains the alpha hydrogens. Okay, so this is the, this is a CH3, so all 3 have an equal probability of being an alpha hydrogen. I only circled 1 just for reference. Okay, now all 3 are alpha hydrogens, and on this side, both of these can be alpha hydrogens. Okay, and 1 adjacent to alpha is your beta carbon, and that's, so this is your beta carbon, so this is your beta hydrogens, and this is your gamma carbon, so this would be your gamma hydrogens. Okay, alpha, beta, and gamma. But say you have an alkyl halide like what we've been discussing. This is the carbon containing the leaving group, which is the Br. Because it's not a double bond, this carbon still has 2 hydrogens, and that's alpha. And this is the adjacent carbon to the alpha carbon, so this is the beta carbon. So this is the beta hydrogens. This is the gamma carbon, so this is the gamma hydrogens. Okay, similarly, if the Br is in the middle, that means the hydrogen attached to the leaving group, carbon containing the leaving group itself, is the alpha carbon, so this is the alpha hydrogen. And on either side, wherever your alpha carbon is, if your leaving group is sandwiched, that means on either side you have beta carbon, and beta carbons contains beta hydrogens, and on this side this is a CH3, right? So again, all 3 are beta hydrogens. Okay, and on this side there's no more beta. If there is a carbon, that would have been gamma, but there is none. But on this side we have our beta carbon containing the beta hydrogens, and then you have your gamma carbon containing the gamma hydrogens. For elimination reactions, typically for alkyl halides like what we are focusing, I'm only going to star these because this is a completely different area. However, I would like to point out, because there are differences on where the alpha hydrogen is located, right? So whenever an elimination reaction happens, this beta hydrogen right here, okay, the beta hydrogen is what normally comes out, okay, because your nucleophile attacks the beta hydrogen, and then in the process you lose your leaving group. Okay, in the process you make a double bond. I'm going to show that with an actual example. Okay, but for now just bear with me, and then we're going to just understand where the beta hydrogen is. So the take-home message here is, it's the beta hydrogen that is lost during elimination reactions. Whether it's E1 or E2, it does not matter. Okay, it is usually the beta hydrogens that is lost. So the take-home message is beta hydrogens is typically lost. All right, I'm going to stop the video here because of time constraints. And in the next 2 videos, I'm going to walk you through elimination reaction 1 and elimination reaction 2. All right, so stay tuned.